Welcome to the topic of direct volume rendering part 2. Today I'm going to talk about how to implement the optical model we discussed last time to achieve volume rendering. First of all, I want to remind you how do we perform integration. So let's look at the left-hand side of this image. Suppose we want to calculate the total area behind this function curve. One way to do this is divide the domain into many small subsegments. Here, I represent the segment as x0, x1, x2, etc. And then we can assume that this area under the curve being divided into small rectangles. And then we evaluate the function value at those direct points, and we add all those small rectangles together to approximate the area under the curve. Obviously, this is very rough approximation. However, as you divide the domain value into smaller and smaller pieces, your result is going to be more accurate. And this is typically called Riemann sum. So if you look at the right-hand side, I can write the equation of integral from 0 to d. Suppose I want to integrate the function value of h over x. Now I can approximate this integration by dividing the value range x into many small subsegments. Here I use delta x, and I have n segments. And I evaluate the function h at each of the sample values xi, and I simply sum the function value, multiply the width of the segment delta x together to approximate this integral. There are so many ways to perform numerical integration, and this is not necessarily the most accurate way, but this gives you an idea how you can simply perform numerical integration. So knowing how to calculate integral using Riemann sum, now let's look at how to evaluate the volume rendering equation. So let's pay attention to this exponential term that represents the decay of the light due to occlusion from the particles in front of a current light source. The light source can be the background light or can be a particle that emits light. So how do we compute these exponents? So using the principle of Riemann sum, we can divide the range of t from d to d, that is how far the light travels, into n small pieces. And each piece I have a width of delta t. And then at the center of each piece, I evaluate the function tau. So this center point, I make that ti. Now, because this t or ti is just incremental advance of the ray, so I can simply replace that with a integer I from 1 to n, multiply my step size. Here I use the symbol of delta x. So each ti is a I times delta x, and the delta t I just simply replace with delta x. So after we have the sum, we can replace this e to the power of the sum by a sequence of multiplication. Each turn, we evaluate the tau function for the input parameter I times delta x. Remember earlier I say this e exponent is related to transparency. That is, how much light is allowed to go through. And it is equal to 1 minus the opacity, or alpha. So I can replace this multiplication sequence of e to the power of minus tau delta x by 1 minus alpha I, where the alpha I is the opacity for every sample point along my ray. So basically, if you start the light source in the very beginning, after it goes through n particles, and each particle has the opacity alpha I, only the multiplication of 1 minus I from all particle, this much of the light is going to survive. So then let's go back to this volume rendering equation. The first term is absorption, of the background light. The second term is the emission from the particles. And each particle, the contribution is going to go through exponential decay due to the particles that are located in front of it. So we can now replace this integral in the first term and also the second term by a sequence of multiplication. And from our previous slide, you know that this multiplication is a sequence of 1 minus alpha. That is, suppose you sample the ray at n positions, and each position, you know the opacity is alpha, and basically the person tells you how much of the background light is going to be able to go through. The amount of decay can be approximated by the sequence of multiplications 1 minus the opacity. You can imagine conceptually each particle or each sample point allows 1 minus alpha amount of light to go through. When you go through a sequence of those blocking material, the end effect is a multiplication. Now the second term, I replaced exponential. Again, that is a decay due to particles in front of a current particle in question by a sequence of multiplication. And that is every particle in front of the current particle will only allow 1 minus alpha of light to go through. The amount of decay or the number of multiplication you have to go through depends on the position of the particle. Here you see, suppose for a particle like contribute Gi emission energy, then it had to go through from the particle I plus 1 to particle n. So this is actually why this index, starting from the immediate particle after you encounter this current particle Gi, all the way up to the last particle. So you look at this view example in the back, this is our setup. The first particle from the behind, or the first contribution of the light source from the behind is G1, then G2, then G3, and G4, and so on and so forth. So suppose you are trying to calculate how much light from G5 is going to contribute to the final energy plane. You have to go through the exponential decay due to G6, G7, G8, etc., all the way to Gn. And this is actually why the decay multiplication always starts from the next particle, that is index I plus 1, assuming the current particle you want to see how much light can survive is I. Now, so really to implement volume rendering, for every pixel, you cast a ray. And then you sample the volume data at discrete locations, and then you evaluate this equation, which consists of multiplication and addition, etc., to approximate this exponential decay. Now, what you can see is that for every particle Gi, you need to multiply by a sequence of multiplication of 1 minus alpha I for the particle in front of it. So there's a lot of actually repeated multiplication of 1 minus alpha I. So an efficient implementation of this is to write this in this nested form. That is, I'm going to composite, that is, blend the effect of the light opacity from the back all the way to the front. So let me explain this long nested equation in the next slide. So basically, the reason I write this equation in this form is that I can perform computation in a nested manner to avoid unnecessary and redundant computation. So starting from the very back, you have background I0. Typically, this is set to 0. Then you are going to add a contribution from the first particle. You can imagine the particle here, I mean the sample point, G1. Then how much is survived? You first multiply 1 minus alpha 1, which is its own opacity contribution. Next sample point, G2. You add the G2 and multiply by 1 minus of its own opacity. And so on and so forth, all the way you finish the ray when it arrives at the image plane. Later, I'm going to show you actually as we perform volume rendering, we don't cast ray from the background. We cast ray from the pixel into the scene. But we are going to use the same equation with slight modification, and I'm going to talk about it. Okay, so now let's look at the volume rendering algorithm, because essentially we are casting the ray into the volume and sample the data point. So I call that ray casting algorithm. For each pixel, you cast a ray into the volume. And then along the ray, you start to sample data values, say at fixed distance. Of course, if the distance is big, you're not going to produce a good quality of image. And if you take too small simple step size, your volume rendering is going to run very slow. The data value at each sample position is obtained by linearly interpolating the cell corners values, because we need to look at the data value as an image, so we have to convert the data value to optical properties. This includes the opacity we described in the previous slides, and also the color. So you can imagine the opacity is alpha, and the color is the G function value in our rendering equation. And the ray will continue to march into the volume, and you are going to encounter color and opacity at every sample point, and you need to blend them together. Here we call that compositing. When you reach the end of the volume, your ray can stop, and then you return the final color back to paint the pixel. So at every step of your sampling, you need to perform shading and classification. So what is shading? Shading, if you have taken computer graphics classes before, you know shading is basically to compute color, the illumination for a given point. The shading here is going to be done based on the data value you sample from our volumetric data set. What is classification? Essentially, the classification is to decide what material this current sample is in. In the current context, I simplify the task of classification. So what I'm going to do is to compute an opacity for every sample value in the volume. Basically, for things that you do not want to see, you can set it as transparent. For feature that you want to enhance, you increase the opacity value. And this is the classification step. Deciding the color and the opacity for every sample point is typically done through a table lookup. And this table is called transfer function. In the figure here, you see I convert every f of xi. Here the x is the location, f is the data value, and then I convert that into c, which is the color, and a, which is opacity for this sample position xi. Now let's look at shading. Remember, at every point, once you get a value, you need to compute the illumination. Mostly this is the color. If you have taken computer graphics classes before, you know there's something called phone illumination model. So basically, it considers how much of this point is going to receive light from the light source. It is basically divided into three terms: the ambient light, diffuse light, and specular light. I won't be able to give you a detailed description about the shading model. Let me briefly describe the formula. So the first term is the ambient light, which is just basically a constant light contributed from the light source. Here, the C of xi is the color of the point. After you get the data value for the point, you perform a table lookup to see what color you are going to use for this particular data value. And this IA is called ambient reflection coefficient. It's just a constant to determine the strength of this component. you want to add to the final color. The second term is called diffuse light. Diffuse light is determined by the angle of the point with respect to the light source. If the point is pointing toward to the light source, you're going to have more contribution. That is, you're going to be brighter. If the direction of the point is pointing away from the light source, you're going to receive less contribution, so the point is going to be dimmer. This modulation of the direction is computed by a dot product n dot l, where n is the normal. The normal is the orientation of the point, and l is a vector from the point to the light source. C of xi is the same thing, it's a color you want to assign to this current point's data value. And the ID, again, is a coefficient you want to determine how much contribution you want this term to add to the final color. The third term is the specular effect. Specular is determining whether the light is highly reflective. So you can see a bright spot at this point. This R dot V, R is the reflection of the light, and V is the direction from the point to the eye position. When the angle between R and V is larger, you don't receive much reflection. When the angle phi is smaller, look at the figure at the bottom. When the angle phi is smaller, you receive more. So R dot V is to modulate how much reflection you can see. And again, the C over xi is the color you want to assign to this particular point. And the is is the coefficient you want to use to determine how much contribution you want this part of energy to the final point color. So this is a very brief description of the phone illumination model. This is one of the main subjects in computer graphics class, but really the equation is not that complicated. I'm hoping you get the gist of it, even if you did not have computer graphics classes before. So one thing important for us to calculate shading is to know the vector n, that is the normal. What is the normal? Normal is the orientation of the point you are sample. You can imagine this is approximated by the gradient. So in order to get the lighting for a point, you need to compute the gradient. And this gradient is used as the normal direction. Let me flip back to the previous slide, and you have normal here. And from normal, you need to derive R. And so normal is an important property. And that is approximated by the gradient value, which is a vector. So given a point in the volumetric space, say xyz, how do you calculate the gradient g? There are many ways to perform this numerical gradient calculation, but one popular method people use is called central difference. Essentially, for every grid point, you can calculate the gradient using the central difference formula. Here, xyz is the position of the gradient. And then, for any point inside the cell, you can calculate the gradient at the grid points surrounding the cell, and then interpolate the gradient. Remember, gradient is a vector that has 3 components for our 3D data. So as you're interpolating the gradient from your 8 corners of a cell, you need to interpolate each of the 3 components separately. Okay, so the shading is to evaluate the color. So you can imagine this is the G function here. Next, let's turn our attention to classification. So that is, we need to evaluate this multiplication sequence of 1 minus alpha I. In order to do that, we need to know the alpha value. So how do you determine alpha value? Alpha value is the opacity value assigned to each sample point. The general rule of thumb of assigning this opacity is to give a higher opacity to region of interest, and the rest you give a translucent or transparent property. And this opacity is typically determined by a function called opacity function. Sometimes people simply call that transfer function. It's a lookup table, which is typically given by the user. I will talk about the design of transfer function in a later lecture, and this is actually an important topic for volume rendering, because only by providing an appropriate transfer function, you can identify important features from your data. Now let's move on to resampling. Just an overview. So you basically cast the ray from your camera position through the pixel center. For each pixel, you sample data point from the volume. In this example, I collect color C1, C2, C3, and I'm also going to collect opacity for each of the sample points. The value of the sample point is obtained through trilinear interpolation. This is linearly interpolated data value from A corners of a cube. I'm assuming we are using regular cube data. And then I'm going to composite the value C1, C2, C3 to blend them together along the sequence of the ray. One thing to keep in mind that you have to follow the strict visibility order. That is, you have to combine value of C1 with C2 and then with C3 and in a sequence. You cannot scramble the order. Otherwise, you're going to get incorrect image result. How do you perform back to front? This is essentially to implement the nested equation I just showed you earlier, but now we can focus on individual step. So initially, I'm going to assume the pixel color is black before I obtain any contribution from the volume data. Then I'm going to get the value C1 and the alpha 1 for the first point. And because initially my pixel color is black, so I'm going to add the contribution of the first point to a black color. So here I'm saying the new color C is C1 under the black color. Under means that initially is black, C1 is behind the black pixel. And I obtain the color to C1. Now I advance my array, I encounter new point C2, and I'm going to add the C2's contribution, and C2 is behind my current ray up to before the second point. So I'm going to use equation to blend C2 under the C. Then I move on to the third point. I'm going to blend the third point's color opacity under the ray. And you keep going and so on and so forth. This under operator tells me how do I add contribution from a point that is behind what I have seen so far. And this formula, this under operator, can be evaluated using this formula. So what does this formula say? Basically, when I encounter a new point, I convert to alpha, that's the opacity, and convert to color for this new point. Then I assume before I see this point, I have a color accumulated so far, called C in. And this input color is going to be affected by the new contribution. So I'm going to multiply 1 minus alpha of this current point plus the color from the current point multiplied by its own opacity. And the result gives to C out. So this is the color, the new color I obtained after consider 1 point further down the ray. Sometimes people call this alpha blending because we are blending a sequence of semi-transparent points. There is another way you can use to perform image compositing by using so-called over operator. Using this over operator, you're assuming you start with an initial color, And then you blend this initial color over the first sample you see. In this example, we use C1. Then accumulated color, you save it. Then you continue to march your ray. Then when you see the next point in C2, you blend the accumulated color and opacity so far on top of C2, that is over C2. And you continue the ray and you start to blend on top of the next sample and the next sample and so on and so forth. To implement this, you need to use the equation in the red box here. So the difference here is that you have to also store the accumulated opacity up to the current point. If you go back to the previous slide, you're going to find out that using the under operator, you don't need to store the alpha that is accumulated. Now, this equation, the CL is the result after you blend the new sample. The new sample has color C of X. X represents the point you are seeing right now, and alpha of that point too. So you take the input color from the previous step that you accumulated so far. You add the contribution of this new sample. Essentially, this is the color multiplied by its opacity, and then multiplied by the accumulated alpha up to this point. And you get a new color, and you update, that is, you take the current sample into account, update the opacity, that is the alpha out, and you send this C out and alpha out to the next iteration. If you do this over, sometimes people call that front to back compositing, you should be able to get the same result as what you will get using back to front equation I showed in the previous slide. The difference here is that you keep track the accumulated alpha. So sometimes you can perform so-called early rate termination. That is, once you realize the alpha out is equal to 1, you can stop your rate. There's no point for you to keep going because future sample will not contribute to the final image at all. Why? Because you look at this 1 minus alpha in. 1 minus 1 equal to 0. So the new sample will always be excluded from contributing to the image. And same thing for alpha. If the accumulated alpha is already 1, 1 minus 1 equal to 0, you're not going to add any new contribution to the accumulated alpha. Okay, so this concludes the discrete implementation of volume rendering algorithm.